Muy bien, estamos llegando al final de nuestra sesión, nuestra primera sesión del Congreso y, como os decía esta mañana, creo que ahora tenemos una ponencia de altísimo nivel. Va a estar con nosotros uno de los padres de la inteligencia artificial, tal como la conocemos hoy en día. Él es profesor de Computer Science y Statistics en la Universidad de California, Los Ángeles. Es un científico, además, que bordea en su actividad, ¿no?, aspectos humanistas, como se interesa por temas relacionados con la filosofía de la ciencia, el razonamiento humano, y además, a lo largo de su carrera ha recibido multitud de reconocimientos, multitud de premios. Destaca, por ejemplo, el premio Alan Turing, que recibió en 2011, y también recientemente, en este mismo año, en 2022, ha recibido el premio Frontera del Conocimiento que entrega el BBVA. Él nos hablará desde California. I'm going to introduce you, Professor Pearl. It's a big honor for us to have you there. We really thank the early morning that you are taking. Here in Barcelona, it's evening. So we will be very, very pleased to hear you. And whenever you like, you can go ahead. Thank you very much.
Well, thank you, and welcome to California morning. It's a great pleasure for me to address this conference or your Congress, and I'm going to talk about the transition from causal inference to data science, to the future of data science. And what I would like to do in this short presentation is to talk about the tension between the two worlds of data science. It consists of two worlds, data and science. And I see a great tension between the two worlds. I'm not happy with the way that data science is going today, and I'll try to convince you that we should do more science and less data. So my outline will talk about first two revolutions. There will be a big data revolution whose success we know very well, and it is in the public eye. But I'll talk of some of the limitations, and primarily its tension with what I call the causal revolution. The causal revolution talks about the transition from data fitting to data understanding. I'll spend a lot of time defining what I mean by understanding, and then what do we need to achieve a level of understanding from the data. So my third point will be to describe to you the Rosetta Stone of causal inference, which is a ladder of causation. It's a hierarchy which lets the investigator know at what kind of task he or she are performing and where in the hierarchy one is, which tells you what kind of data is capable of delivering the answers to one's scientific questions. Then I'll talk about 7 wisdom of causal thinking. These are the tools or the achievements of the causal revolution, which are tools that allows you to answer scientific questions using the data. And future direction, if I'll have time, I'll speak about the aspiration of achieving an automated scientist on one hand and going from population to individual decisions so that we can do beautiful things like personalized medicine and situation-specific decision-making. I'm going to here start with the data science. I see it as a clash of two paradigms. On the data-centric paradigm, we have the belief that all wisdoms comes from data, and our job is to fit the data so as to maximize some goodness of fit measure over the data itself. And it is contrasted with what I call the scientific paradigm. And I'm going to display to you what I mean by scientific paradigm, which, as you see, is totally different from that data-centric paradigm. It answers the question, what should be the world? So that I can answer a question about the world. It hardly talks about the data. It's using the data as an instrument to answer questions about the world. And that will allow us, focusing on the world, will allow us to extract understanding from data. So now I'm going to define what I mean by understanding. First, before I get to understanding, I'll go to the scientific paradigm. And this is a flow chart describing to you the methodology of science. At the heart of the problem, you have a model of the world or of reality. But we don't have a face of reality. We don't have reality itself. We only have our model of reality, and that's why I call it M, a model of reality. In many cases, we don't even have the model. We have only a partial model. It's our perception of reality. But we are not going to give up just because we are missing few elements from our model of reality. In the heart of the problem, we have a query, a question we want to answer about the world. For instance, how can we do things in order to achieve a certain result? That's in the world. And we know that we have data with the help of which we are going to answer this query. So this is the input. We have query, we have a partial model of the world, and we have data to help us. The way we go from this input to the output, which will be a solution, is going through calculus, which is a mathematical object, which contains a logic of going from these three inputs, data, query, and partial model, to the solution that we are requiring. And the problem we said to be solved or solvable if my model permits the calculus to express the query, you see here the query, in terms of the available data. And the available data will be either observational data or a result of experiment or result of several experiments, each coming from different environment upon which we train the machine and answer the question about what? About the query. And I repeat and I emphasize again, the query is about the world, not about the data. This will be the difference between the way that data science is practiced today, where all the queries are about the data, and the scientific paradigm, where the queries are about the world. Let's see what we mean by understanding by looking at some typical problems whose solution requires understanding. Let's look at the typical question. And here I put 5 examples. How effective is a given treatment in preventing a given disease? Another one. Was it the tax breaks that caused our sales to go up or our marketing campaign? You can see how important it is to design our next season campaign if we know what caused our sales today to go up? So that's a question about going back in time. And the third one, what is the annual healthcare cost attributed to obesity? Fourth, can hiring records prove an employer guilty of sex discrimination? That's a question of assigning credit and blame. We call it discrimination to and on the basis of the hiring record, which is our data. Okay? And I'm going to the fifth one about personal decision making. I'm about to quit my job. Will I regret it? Okay? Now, as you see, I marked here, I colored these words in yellow for a reason. They are special kind of words. I recognize them from 5 miles away because I've trained myself to look for them in every sentence that I say and find out something very peculiar. They cannot be answered using the tools of ordinary science. Ordinary science have not been gracious to us to provide us the ability not only to answer those questions, but even to articulate them in any formal way. Why? This kind of relationship cannot be captured in the standard grammar of science, and I'll tell you why in one line. Because the grammar of science is restricted by the equality sign. The equations of physics are written in terms of equality. For instance, Newton's law, F is equal to ma, and the equality sign is symmetric. So if y is equal to ax, then x equal to y over a, and there is no directionality to the equation of physics and the laws of physics. So this ought to be different because all these relationships have directionality. I'll give you the examples which I like most. It is the relationship between the barometer deflection and the atmospheric pressure. Okay. The equation of physics are written in equality terms, and they cannot capture the asymmetry that you and I understand in the relationship between the atmospheric pressure and the deflection of barometer. You and I understand that by moving the barometer, I'm not going to change the atmospheric pressure, and I'm not going to make the weather tomorrow different. But it's the other way around. It's the atmospheric pressure which is causing my barometer to change. But how do we tell a robot that if we plug in only equality relationship, we cannot tell the robot that by moving the barometer, he or she cannot change the weather tomorrow? That required a new operator, an assignment operator, which tells you that nature looks at the atmospheric pressure, does some computation, and then assign the value to the barometer according to those computations. So it's really an assignment operator, which we sometimes denote by arrow, and that's the reason why we have arrows in the graph. Sometimes we write it in computer science in the form of an assignment operator. Take the content of register A and plug it into register B. And that kind of assignment operator is the heart of everything I'm going to talk about. It's the heart of causal reasoning. It's augmenting the laws of physics with an assignment operator, and thus introducing asymmetry that captures the directionality of causal relationship. Okay, what do we do with that philosophy? We have to get down to a computation. And I just want to pass and tell you that I view it as a new dimension. A new dimension where science up under equality sign reflects shadows, two-dimensional shadows of the real object, of real reality, which have to do with three-dimensional objects. It is three-dimensional objects which are being projected here onto the screen of shadows. And we are looking, I mean, if we do statistics only, and we're looking only at data, we are looking at a projection of reality onto a lower dimension world. We have to infer from that the existence of the three-dimensional object and their property. It's just a metaphor. But now let me go closer into this transition, the sharp boundary between statistical and causal relationship. Here are examples of causal relationship. We have spurious correlation, randomization, intervention, fixing something, confounding. All those are causal relationship, and those are associational. Regression, independence or association, controlling for or conditioning on variable, all that you can find in the literature. And here is a dichotomy between causal and associational. The dichotomy is very clear. Those relationships cannot be articulated with the language of statistics, namely with the language of probability distribution on observed variables. You need something more if you want to define any of these terms. And it was captured very nicely by Nancy Cartwright in 1989. She said, no causes in, no causes out. If you want your conclusion to involve causal relationship, you must have some causal information in the input. Data itself is not sufficient to give you causal conclusion. You need to have either causal assumptions or experiments. And now the duty, the task of causal analysis is to combine the two and produce causal conclusion. And that also tells you that the causal assumptions cannot be expressed in the mathematical language of standard statistics. Because if we were able to express those causal assumptions in the language of statistics, then we will be able to get data alone giving us the results. But this rule says no. Therefore, we must have a new language to capture this additional information, which I call causal information. Causal information is preserved, or conserved, like the conservation of energy and momentum in physics. So we need a non-standard mathematics. And where this non-standard mathematics come in, it comes from structural causal model, which I'm going to define in a minute. It goes back to the geneticist Sibyl Wright, who in 1920 had the audacity to use an arrow. He was the first one that captured the asymmetry of causal relationship in terms of an arrow. It's a new mathematical object, and wrote down y is equal to f of x, meaning that this equation is not really algebraic equality, but it is an assignment operator. There were other attempts of that sort in philosophy and in statistics, but he prevailed in the sense that today we are using causal graph to articulate this asymmetry that we find in causal relationship. Let me show you how it works. Here's the causal revolution, and I'll explain to you where I take the audacity to call it a causal revolution. Gary King, a political scientist in Harvard, articulated in those words. More has been learned about causal inference in the last few decades than the sum total of everything that had been learned about it in all prior recorded history, which is quite a sweeping statement. And I'd attribute that revolution to the fact that we computer scientists were able to take the needed language and treated it as a new language with new semantics, new notation, and new understanding. So that is the reason for this sweeping advance or revolution, let's call it, okay? You can tell the revolution in quantitatively in the way that causal papers appeared in statistical conferences. There were 13 papers only that had the word causality in the abstract in 2003, 130 in 2013, and today you have dozens of causality-specific workshops and conferences in many, many communities. So that is a quantitative measure of how prevalent the understanding is that we need to capture causal relationship. We cannot leave it as we did in the past to the mercy of equality sign or to the mercy of statistical relationship. It's fun and it's profit, and I want to convince you that it should capture and penetrate our education as well. And it's fun also because it captures the human mind and allows us to answer questions about how our mind works, because after all, this mind of ours is a causality machine. It's not a statistical machine. Again and again, you can see that most of our language is sprinkled with causal relationship, not with statistical relationship. We hardly can perform the logic of statistics in our mind, but we are very good in performing the operations that are responsible for causal relationship. To deduce output from input, if you have causal input, deduce the causal output. We are very good at that, not too good in capture. So by capturing those relationships, we are really learning about how our mind works. And that's the most fun I find in this work. Okay, this is now the ladder of causation. And this is the hierarchy that we found mathematically. This is a mathematical statement. If you look at the kind of relationship you find in your language, you find that they are divided into three levels. At the bottom level, you find seeing, which tells you, what if I see things? What can I expect in the future if I see something in the present? For instance, how would I change my belief in X in Y if I see X? Examples, what do the symptoms tell us about the disease? Or what does the survey tell us about the election results? I picture it in the form of an owl and a robot, because this is where data science is today. Why I put an owl there? Because owls have developed very keen vision system. It tells them how to predict the location of their prey if they see the prey moving in a certain position. And robots are today in the same stage as the owls and the eagles. But owls did not invent microscopes and telescopes. We human beings did develop that, not even eyeglasses. So the next level is about intervention. What will happen in the world if we take an action and we intervene? For instance, if I take aspirin, will my headache be cured? Okay? Or what if we ban cigarettes? Why I put this example? Because we haven't been trained. We haven't seen such an action before. No society has been able to really ban cigarettes. And still, we are able to predict what will be the world like if we succeed in banning cigarettes. So here's an example of contemplating the results of an action that was not seen before. And the top level has to do with counterfactual, it has to do with imagination, retrospecting, and understanding. This is the level where we operate today. This is the level where scientists operate today in their everyday life, not science, because science has been handicapped by the equality sign. But physicists write equalities and they think causal relationship in the cafeteria and in their conversation and in their mind. So here's an example. What if I had done things differently than I actually did? Related is, was it X that caused Y? Going backward, seeing why an event and asking what caused it. An example, was it the aspirin that stopped my headache? Or perhaps other things? Perhaps the good news that I saw on television. Would Kennedy be alive if Oswald had not killed him? Going backward in time after seeing the results. Okay, now it so happens, mathematically speaking now, that you cannot answer question in level I unless you have information in level I of type I or higher. You cannot answer question about intervention unless you have information of type counterfactual or in terms of result of intervention, but not enough to have only information from level 1, which is seeing, observing, namely statistics. So this is the Rosetta Stone to tell you at every level of your analysis what kind of data you need, where to find it, and whether your task is doable or not doable. I'm going now to tell you something which I think is the two basic laws, two fundamental laws of causal inference, that if you have them, everything that I said, and everything that I've done in my career can be derived mechanically and needs no help whatsoever. This is the fundamental law of counterfactual. It tells you that every counterfactual sentence can be assigned a truth value given a model. The model is a collection of functions. Now, the rule here says that the counterfactual, what is the value of y had x been small x? Had Cleopatra had a longer nose, what would be the world like? I can compute it, I can assign to it a truth value, yes or no. If I have a model, all I need to do, take the model, look at the equation of x here, remove it, replace it by a constant. What is u? U is the specific conditions under which you operate, or the unit of computation could be an individual name, a person, and so on. So this is the first law that defines all the operations that are needed in causal inference. Here I am. The next one is the law of conditional independence, also called disseparation, that many of you have learned if you took a class in graphical analysis. It tells you that if you look at your graph, what is a graph? A graph is just an abstraction of a collection of functions, where the arguments are the parents and the output is the son. So now you look at the graph, and every time you see a separation in the graph, two things are separated, it implies conditional independence in the data that you see. So that allows you to, What? 5 minutes. Okay. Good. Okay. I'll go very quickly and just entice your appetite, just to show you. Here's an example of a model, collection of functions. You don't know the function, but you only know who the arguments are and who the beneficiary is. And you can compute conditional independency in the data once you have the structure of the graph. It allows you to trim the collection of graphs and can do causal discovery to discover the structure of the graph or a set of structures based on the data and many other things. But let me go quickly because I have only 5 minutes. So I'll go into the 7 wisdom or tools of causal inference. What can you get from all this philosophy and the 2 basic principles? Number 1, and don't underestimate its importance, we can encode causal information in transparent and testable way. Tool number 2, we can predict the effect of actions and policies on the basis of that model, or our perception, or our partial model. 3, we can compute counterfactual and find causes of effect and lead us to attribution, assigning credit and blame, to explanation, to susceptibility. Tool number 4, we can compute direct and indirect effect, also called mediation. We can distinguish direct and indirect effect, which allow us to handle important problems such as discrimination, inequalities, and fairness, which is much in the news today. Everybody wants to have a fair algorithm. Tool number 5, we can integrate data from diverse sources. It is also called fusion or transportability. In machine learning, they call it transfer learning, but in machine learning, transfer learning is only an aspiration. It is not a tool which can be proven to be working. In causal inference, transportability is a complete field which gives you a complete result under certain conditions. At least it tells you when your results are guaranteed to deliver what you wanted to deliver and when it's not enough. So here we have 5 tools. I'll talk with the 6th one, recovering from missing data, which turns out to be a causal question because you need to have the reasons for missingness, and you cannot do it with pure statistics. And the tool number 7 is causal discovery, which I mentioned lightly, the idea of finding the causal structure based on data only. I think I have only 2 minutes, so I'll summarize it with, oh, look what you're missing. But all of these nice things are discussed in my book, Book of Why, so you can read it at your leisure and find out my conclusion, which is that, here's my conclusion. The next revolution will be even more impactful once we realize that data science is the science of interpreting reality, not of summarizing data. So this is my conclusion. I think I'm, yeah. So what is causal inference? It's a leverage that elevates data science from the level 1 of the hierarchy to a higher level, rank 2 and rank 3. From data fitting to deep understanding. And I want to thank my co-workers, my students, reviewers, co-principal investigators, and end up with a sentence that I love from Augustus de Morgan, the same de Morgan that we have de Morgan law in logic, contemporary of Boole. And he said, every science that has thriven upon its own symbols. And causal inference is a science of new symbol, the symbol of an assignment operator, notated by the arrow and the causal graph associated. Here I am, up, and here's my sales pitch. You can read all of it in the Book of Why. I hope you do, then we can communicate with a richer vocabulary. Up, I think I'm done. Thank you. I'll be happy to answer any questions that you have.
So, if there would be any question from the audience, I think still we have some times. There is no, oh, there is one question up there.
Good evening, Professor Perl. Thank you very much for your conference. My question maybe is not very important. It's only if you need to explain the problem through causal inference, there is any implication for the training if you need an analytical function at the end or a derivable one to train the system?
I didn't quite understand. Analytical function?
Yes, that you can derive the function to train the system, to make a regression with gradient.
You mean whether the function that stand behind the arrows needs to be of special kind? Is that the question? Or we don't need to know the functions. Normally, we don't know the functions. We know only who is the arguments, what variables are the arguments, and what variables are the output. We don't know the function themselves. But we make up for this lack of knowledge using the data. So in most of my work have to do without the functions. Only when I need to do the highest level of counterfactuals, I need the properties of those functions.
All right, thank you.
Thank you very much for your presentation, Dr. Peel. My name is Ray. I'm from Butler Scientifics. I would like to ask you, I am especially interested in automating data science pipelines. And I know that automating is hard work because it implies a lot of human brain activity and decisions. But what do you think about automating causal inference? Do you think is that possible? Are we close? What will we need to be able to automate at least partially the process of causal inference?
I didn't get the key word. The properties of, could you repeat the last two words? Counsel, you said.
Excuse me?
The last two words I didn't get.
Okay, so the question is whether you think if it is possible to automate the process of causal inference, to automate it.
Causal, absolutely. I mean, a lot of it is already automated. But when we talk about automating a scientist, that is a future task. We need to have a system that decides on its own on the next experiment to conduct, given a certain query. And that requires a higher level of reasoning, level 3 of the hierarchy, and what information to buy when we are stuck and we cannot deliver an answer to a scientific question. Yes, most of it is already automated, but bits and pieces. Now we get to integrate them. We need to integrate them all together to be able to answer a harder question that the scientists answer in everyday life. The most important is, what is the next experiment to conduct? What is the next observation to buy, to acquire, in order to answer questions which cannot be answered with the available data that we have? Yes, I think that automated scientists will be a task that will be achievable in the next decades.
Great, thank you very much for your answer. I hope I can work close to you at any time.
Thank you.
There's still another question from the audience.
Hello, I'm Mercè Crosas. I was at the Harvard Institute for Quantitative Social Science with Gary King for 20 years. Gary King has been one of my mentors at Harvard. Thanks for citing him. But I was going to ask you a question related. So now, after being 30 years in the US, I have moved back to here. And I noticed that there is less quantitative social science applied methods and causal inference in the education, at least as my experience at Harvard and institutes like the quantitative social science, right? So I wonder, what are your thoughts about how to bring, I mean, at what level we should bring the education of causal inference to the schools, to colleges, to data science masters or PhDs? What is the right level? Because for me, I mean, I agree completely. Of course, I'm completely sold on this after so many years working there in causal inference. But I completely agree that at the end, we're only data science is only going to be valuable if it's based on, I mean, if it can explain the why, right? If it helps us understand, not just summarize the data. So any thoughts on how to bring this here in Barcelona, in Catalonia, and at what level to teach it, and at what disciplines? Thank you.
Yeah, you ask three questions you ask. At what level to introduce causal inference? And that the answer, you can introduce it in high school. I have two students who introduced a causal inference class in their high school, and the students love it. Why? Because children think cause effect. They don't think statistics. So if you start at a high level, it will be much easier than the kind of curriculum that we have today, which are built on statistics, and students have to learn test of hypothesis and regression. It's not natural. Causal inference is natural, it's human. So we start at high school level. Number two, the question is, in what kind of perspective? And here we have competition with various ways of introducing causal inference. The worst thing is to go to machine learning, because machine learning have all the clouds and they are sucking the oxygen out of education and for funding and public attention. They all built essentially on data feeding. So this is the wrong way of introducing causal inference to education. There are other competitors, but I wouldn't argue. I just published, we just have 4 monologues published in the Journal of Observational Studies. Jim Heckman and Rubin and Robin and myself, each describing his own perspective on causal inference. So you can see the differences and the discontent and the disagreements between the way of introducing. Of course, you know my bias. My bias is to introduce it through the first law of causal inference. This is a collection of functions, a graph which is an abstraction of this model, and everything goes by graph. Both undergraduate students, graduate students can grasp it extremely well. It is a complete and coherent body of logic that we can speak and introduce, and it unifies all the perspectives. So I'm biased toward a graphical approach. I hope I answered the question. Yeah.
Thank
you. You can learn from previous experience of social scientists. Yeah, but when you go back to the history of social science and you ask yourself, what was accomplished there? You find out that they got stuck on various impasses along the way. It's all described in the book. I describe the history of causal inference in social science as well as economics, okay? So I go and describe the traps that prevent them from progress to the level where we have today. And there are many traps. In each field has its own traps. They're all described here in the book of Why. So yes, go ahead and teach social science using Blalog and Duncan and Winship, Morgan and Winship. I'm mentioning few books, but recall that this is a narrow approach. It's all unified in using the causal inference as I presented here in the book of Why.
Okay, so I think that we've got a lot of answers from Dr. Pell. I would like to thank you again. It was a pleasure and an honor to have you here. I can tell you couldn't see, but the audience was very, very much concentrated, trying to capture all the information that you conveyed.
Thank you.
So thanks again, and lot of luck to California. Thank you very much.
Thank you.
Molt bé, doncs amb aquesta classe magistral, jo podria dir, molt intensa, breu però molt intensa, del professor Judea, arribem al final de la primera jornada del Congrés. Avui, jornada presencial, espero que hagueu realment gaudit i après coses i agafar moltes idees de totes les sessions que hem tingut al llarg de la jornada. Recordeu que demà farem la segona jornada del Congrés, aquesta vegada online, i com sempre, abans d'acabar, només agrair dos agraïments. Primer, a tots els membres del CIDAI, a totes les empreses, centres, universitats que estan en el CIDAI, per la seva col·laboració, per la seva predisposició a fer coses. Tot el que hem pogut explicar avui és fruit d'aquesta col·laboració. I el segon agraïment va per l'equip d'esdeveniments, encapçalat per la Gemma López, d'Esdeveniments d'Eurecat, l'equip de comunicació i tot el comitè de programa que fa possible que any rere any realitzem el AI and Big Data Congress. Moltes gràcies, espero que ens puguem reveure l'any que ve. Fins ara.